Yeah, so I hope my screen is visible to everyone. So hello everyone, this is lecture 19 on discrete mathematics, and in the previous lecture we were discussing edge connectivity and vertex connectivity. So what was the edge connectivity? It was the minimum number of edges whose removal disconnect the graph, and size of the smallest cut set, you can say size of smallest cut set is nothing but your edge connectivity. So edge connectivity we have done in the previous lecture itself. I am just going to revise the thing so that we get more clarity. Okay. Vertex connectivity was minimum number of vertices whose removal disconnect the graph or make it trivial. This is very important. Okay, so it can make the graph. We can make the graph trivial also. Trivial means single dot. Okay, vertex connectivity we have done already. Okay, so now we are going to study this thing. Vertex connectivity of this graph. So see this. Is there any cut vertex here? No. So two vertices, you just remove these A and C. Your graph will be disconnected. So vertex connectivity is 2. What is edge connectivity? So you can remove these two edges, or you remove these two edges, graph will be disconnected. So edge connectivity is 2. What is connectivity here? So try to see this. D is cut vertex. Okay, so the moment I remove this, graph will be disconnected. So vertex connectivity is only one. Minimum number of vertices whose removal disconnect the graph. So only one vertex removal can disconnect the graph. Edge connectivity is same. This is cut edge. Okay, ED is the cut edge. So you simply remove it. We will get our answer. Okay, so that's it. So next is vertex connectivity and edge connectivity. And in fact, and one more thing is coming to my mind. You should know this thing. So that this E1 is the cut edge. Okay, because this removal of this will disconnect the graph. Now it is for sure that this vertex A and B will be cut vertices. By common sense you can guess this. So directly what I want to say is, if we have a cut edge, then the vertices joining the cut edge will be cut vertices. Okay, so vertices. Okay, these are theoretical questions, and these questions have been asked in gate many times, so you should remember this thing. And by common sense you can check this out. If in gate exam, if they say which of the following is true or false, so if they give the statement uh, vertices connected to cut edge are cut vertices. Okay, so you just make a graph, and at the same time you will be able to guess, okay, this statement is 100% true. Okay, or you can say vertices of cut edge. Okay, vertices connected, we can say in place of vertices connected, we say vertices of cut edge are cut vertices. Yes, 100% sure. So vertices of cut edge, see, because edge cannot exist without vertices now. So when we have an edge, so obviously it will be joining two vertices. So now these two vertices which are joining this cut edge, they will be cut vertices for sure. Okay, I hope I have made the point clear. Next is vertex connectivity and edge connectivity for this graph. So vertex connectivity can be, so see this, there is no cut vertex here, so we will try to attack the opposite vertices or non-adjacent vertices. So if you try to remove the adjacent vertices, it won't help you. Okay, rather here it is an exception, like A and D. If we remove this A and D, then obviously these two edges will be removed and we will get a disconnected graph. But general sense is that you try to attack the non-adjacent vertices. Okay, they can help you more. Okay, so anyhow I think you have got it. Vertex connectivity is 2. Okay, so you can remove A and D, we will get our answer. Similarly edge connectivity, so you just remove these two edges, you will get the answer. Okay, so edge connectivity is also 2 here. What is vertex connectivity and edge connectivity? Vertex connectivity, so now see the definition. I have told you vertex connectivity, minimum number of vertices whose removal disconnect the graph or make it trivial. So this is a complete graph of 4 vertices. Okay, so now, yeah, since every vertex is adjacent, every pair of vertices is adjacent, we should say like this, every pair of vertices are adjacent. So if I remove D, no, nothing is going to happen. D and B both are removed. Okay, if D and B both are removed, even then AC edge will be there. Are you getting it? So we cannot disconnect it. It's very simple, because it is a complete graph, we cannot disconnect it. So finally we will remove the 3 vertices and we will get a single vertex graph, that will be trivial graph. So vertex connectivity will be 3 here. Okay, similarly edge connectivity, I can remove minimum number of edges which should be removed. So with C, these 3 edges are present, so you can remove all the 3 edges. Now this C and this triangle will be left out. So obviously edge connectivity is 3. Similarly you can check it out for any vertex. Okay, so edge connectivity is coming to be 3. Please let me know if anybody is having any doubt.
Done, sir.
Okay, so please take snapshot. I will jump to the next slide.
Okay, sir.
Okay, So for Kn, vertex connectivity is equal to H connectivity is equal to n minus 1. That is very, very obvious. Okay. So why? Because you have to remove n minus 1 vertices. Now only then you will get a trivial graph. For vertex connectivity, you have to remove all n minus 1 vertices. So for example, triangle, this is K3. So now you have to remove 2 vertices so that you get a trivial graph. Okay. So vertex connectivity will be n minus 1, and similarly edge connectivity will also be n minus 1. Why edge connectivity will be n minus 1? Because if you can pick any vertex, okay, and you remove all its edges, only then you will be able to get that. And every and Kn is n minus 1 regular. Are you in the previous lecture also I have told you. So K4 is 3 regular, na? So you have to delete 3 edges. Without it we cannot do it. So directly indirectly what we can say, edge connectivity and vertex connectivity will be n minus 1 for Kn. So they can ask simple question, edge connectivity and vertex connectivity for K100, you will say 99 and 99. Very simple. Edge connectivity and vertex connectivity of C100, that is a cycle graph. So for cycle graph, see this is a cycle graph of 4 vertices. So how many edges removed will disconnect the graph? A, B, C, D, like this. So you will say you just remove these 2 edges, game over. Or you can remove A and C vertices, game is over. So now try to focus here. Why I was saying that you should not focus on adjacent vertices like BC. You try to remove BC. So B and C vertices. So nothing is going to happen. So better is attack non-adjacent vertices. That will happen. That will help you out. So 2 vertices removal will disconnect the graph. So vertex connectivity and edge connectivity will be only 2 for cycle graph. So for C100 it will be 2 and 2. Any doubt? C100 means 100 vertices cycle. Okay, yeah, you can take like this, you can check like this, any way. Okay, A, B, C, D, E, and F. So you remove A and D, okay, game is over. Or you remove A and C. Okay, I think it is very simple. Okay, take snapshot. I will jump to the next slide. Okay, next. So a very beautiful theorem is coming. It is very important. Vertex connectivity less than equal to edge connectivity less than equal to minimum degree. This is very, very important theorem. Okay, from this theorem you can answer very many questions very easily. So first of all is you should know vertex connectivity will be less than or equal to edge connectivity. Why? Because when we have one edge, then it will connect 2 vertices, na? So directly indirectly edges are dependent on vertices are not dependent on edges. So obviously vertex connectivity will be less than or equal to edge connectivity. Vertex connectivity can never be more than edge connectivity. That means number of vertices are, see, if can I say like this, vertex connectivity is 3 and edge connectivity is 2. If edge connectivity is 2, then obviously there will be 2 edges, na? So you just remove these 2 vertices, you will get the answer. For example, edge connectivity is 2 means like this. These are the 2 edges which should be removed. Okay, these are the 2 edges which should be removed. So now if you remove this vertex and this vertex, game is over. So directly these edges are already removed. So how vertex connectivity can be 3? Okay, so if edge connectivity is 2, vertex connectivity can be at most 2. It can be 1 also. For example, there might be a cut vertex also. See this example, you will get more clarity. See this. So here, this is the cut vertex. So vertex connectivity is 1. What about edge connectivity? You have to remove at least 2 vertices. At least 2 edges to disconnect the graph. You just remove these 2. You will get the answer. One edge removal will not disconnect the graph. Okay. So edge connectivity is 2. So I think you have got the point. So vertex connectivity should be less than or equal to edge connectivity. Vertex connectivity can never be more than edge connectivity. Okay, and it should be less than or equal to delta. Small delta is what? Minimum degree. That is also very obvious point. Minimum degree. Okay, so for example, this is a vertex of minimum degree and this is the total graph. So if you remove these 3 edges, for sure graph will be disconnected. Okay, yeah, so it should be less than or equal to minimum degree. So now you may argue with me, sir, why it is less than or equal to minimum degree? It should be equal to minimum degree. No, because there might be cut edge. For example, here, see this, minimum degree is 2 and you can remove this one edge and game is over. Okay, so vertex connectivity less than or equal to edge connectivity less than or equal to minimum degree. You should remember this thing. Okay, yeah, and same is the case here. Okay, so here it might not work. Minimum degree is 1 and you just remove this edge, game is over. Okay, yeah, but this is the good case. So this is the example which give you more clarity that edge connectivity should be less than or equal to minimum degree. Any doubt?
So here in this example, edge connectivity is
This,
in the second beside example, that side.
yeah, this,
I did not get this, like edge connectivity is less than or equal to minimum degree.
Yeah, so see this minimum degree is 2 here, na?
2.
2, 2, 2, 2, 2, 3, 3. So minimum degree is 2.
Yes,
But
sir.
what is edge connectivity? You just remove this edge. So I can label this AB. So you just remove this edge. Graph is disconnected. So edge connectivity is 1. Minimum number of edges whose removal will disconnect the graph. 1 edge.
All right, so I got confused seeing 3 there. The 3 edges are like which are
Okay,
junction
no,
there.
no, no. This is the degree.
Sir.
Okay, take snapshot. I will jump to the next slide.
Done, sir.
Okay. Yeah, so how to find edge connectivity? How to find the edge connectivity? So try to find cut edge. If cut edge is present, then edge connectivity is equal to vertex connectivity is equal to 1. Why I am saying so? Because vertex connectivity is less than equal to edge connectivity is less than equal to delta. Now if cut edge is present, so edge connectivity will be 1. So vertex connectivity should be less than equal to 1. So obviously vertex connectivity will be 1. Na? 0 is not possible. Vertex connectivity is 0, never possible. That means 0 vertex removal disconnect the graph. That is not possible. Okay, so minimum is 1 only. So vertex connectivity less than equal to 1 means vertex connectivity is equal to 1. Okay, so edge connectivity 1, then vertex connectivity is also 1. Okay, so for sure. So that's why I'm saying try to find cut edge. If cut edge is present, game over. You will say edge connectivity, vertex connectivity is 1 only. Okay, but if cut edge is absent, then find minimum degree vertex. You have to find the minimum degree vertex, and your edge connectivity will be less than or equal to that minimum degree. Okay, so now directly I want to say there is no way out. If cut edge is not there, then you have to do hit and trial. But in place of blindly doing hit and trial, you try to find the minimum degree vertex. Like minimum degree vertex is of minimum degree is 3. So obviously removal of 3 edges will disconnect the graph. But try to find whether can any 2 edges removal can disconnect the graph. You have to check that out. Okay, so basic way is hit and trial. Any doubt here? Please let me know.
No, sir.
Okay, so take snapshot. I will jump to the next slide.
Done, sir.
Okay. So how to find vertex connectivity? Try to find cut edge or cut vertex. If anyone is present, vertex connectivity is 1 for sure. Okay, if cut edge is present, I have told you previously also. If cut edge is present, then vertex connectivity as well as edge connectivity will be 1. So same is the case here. I am trying to say try to find cut edge. If cut edge is present, we will say vertex connectivity is 1. But even if cut vertex is present, it is same is the case. Vertex connectivity will be 1. So for example, this. Here we have a cut vertex. So removal of this will disconnect the graph. So vertex connectivity is 1. Okay, now if cut edge or cut vertex is absent, then attack opposite vertices. I had told you in the previous slides also. Okay, take snapshot. I will jump to the next slide. Done? Okay. Next, edge connectivity and vertex connectivity of a tree of n vertices where n is greater than or equal to 2. So if we have a tree of n vertices, so what is the edge connectivity and vertex connectivity? So you should know a very basic theorem, like you can make any tree, whether it is rooted or non-rooted. Okay, like this, you can make a tree like this. This is non-rooted tree and this is rooted tree. So every edge is a cut edge. Try to see this. If I remove this edge, graph will be disconnected. If I remove this, graph will be disconnected and so on. I think you already know tree means minimally connected graph. Okay, n minus 1 edges are there in, if we have n vertices, n minus 1 edges are there. So obviously even if I remove one of the edge, graph will be disconnected. Okay, so every edge is cut edge. Every edge is cut edge. Okay, so directly I want to say we have cut edges. So cut edges means what? Edge connectivity is equal to vertex connectivity is equal to 1 for sure. Okay, so now I have told you when we have cut edge, then you can say joining vertices will be cut vertices. So like this. So this is the you can say cut edge. So now this vertex will be cut vertex. Okay, this is not the cut vertex, of course, because if I remove this, then graph will not be disconnected. But this is cut vertex for sure. Okay, yeah. So I hope you have got the point that every edge is cut edge means edge connectivity is equal to vertex connectivity is equal to 1, and all the internal nodes, okay, except leaf node, all the internal nodes are cut vertices. Okay, all internal nodes. All internal nodes, or you can say non-leaf nodes. Non-leaf nodes are cut vertex. Okay, so every edge is cut edge, So we have got this point, but just for the sake of completion, or you can say an important point, I'm telling you that all internal nodes or non-leaf nodes are cut vertices in a tree. Okay.
Yes,
Yeah.
sir.
Okay. So take snapshot. I will jump to the next slide.
Okay, sir.
And one more point is coming to my mind. Leaf node. So leaf node degree is 1, na? Okay, because only one edge is there. So if we have a non-rooted tree like this, so I will say node of degree 2 or more than 2, that will be cut vertex. Okay. So directly we are in rooted tree we have definition of internal node and leaf node and so on, but in non-rooted tree we do not say leaf node and internal node. Okay, so better is we will say all nodes of degree greater than or equal to 2 are cut vertices. That's it. Okay. Yeah, take snapshot. I will jump to the next slide.
Sir.
Okay, next. So for a tree, every edge is cut edge and every node of degree greater than or equal to 2 is cut vertex. I have told you this already. Okay, I'm jumping to the next slide.
Yes.
How many cut edge in a tree of n vertices? N minus 1. So simple. Okay. Let me jump to the next slide. How many cut vertices in a tree of n vertices and n leaf nodes? So n minus l.
The previous slide I take comparing screenshot, sir.
Okay. Previous also. Okay.
On the yes.
Then okay. This.
Done, sir.
Okay. Next, application of vertex connectivity and edge connectivity. Vertex connectivity and edge connectivity are quantitative measure of how strongly connected the graph is. Quantitative measure. Okay. So for example, vertex connectivity represents strength with respect to attack on vertices. Edge connectivity represents strength with respect to attack of edges. Okay. So for example, I have made a graph like this. So I will say you can take military application. Okay, so there are 4 bunkers of military and they are connected via these 4 roads. So I will say even if enemy attack on this road, no problem, connectivity will be there. So these bunkers will be connected. Now if enemy attack these 2 edges, then communication is gone. Okay, so vertex connectivity represents strength with respect to attack on vertices. Okay, and edge connectivity represents strength with respect to attack on edges. So it is quantitative measure, na? That means how many vertices should be removed or how many bunkers should be destroyed so that communication breaks, or how many edges should be destroyed or how many roads should be destroyed so that communication breaks. Like this, I think you have got the idea.
Understood, sir.
Okay, take snapshot. I will jump to the next slide. Done.
Yes, sir.
Okay, next. Note, this is very important. There is a limit on vertex connectivity and edge connectivity, that is we can't make an arbitrary large. Okay, we cannot make it like any arbitrary number, like you make vertex connectivity to be 1000, edge connectivity to be 2000, like this. We cannot say like this. Okay, why? Because there is an upper limit, because upper limit is given by this delta. Delta means minimum degree. Okay, upper limit is given by delta. Okay, now but what if graph is not given? Okay, if graph is not given, then how you will say? That is, you are given some wires and computers and I want to find the upper limit. For example, I have given you some computers and I have given you some wires and I want to say that I want to build a computer network, and in such a way that if somebody attack on 2 or 3 computers, then our network should not go down and so on, like this. So they can give requirements. Okay, so now you cannot say that vertex connectivity and edge connectivity can be arbitrary, very large. So let me give you an idea. So take snapshot. I will jump to the next slide. Okay. So see this, delta is less than or equal to 2e by n is less than or equal to delta. So this was known as delta theorem. You may be wondering that why I'm showing you this. Don't worry. Just bear with me for 1 or 2 slides. You will get the idea. Delta theorem we have studied. Okay. So take snapshot.
Done, sir.
Okay, so now yeah, okay, so here itself in slide I have not written, so here itself let me tell you. See this, I have some wires and I have some computers. So computer means nodes and wire means edges. So I have told you that vertex connectivity, the theorem was vertex connectivity is less than equal to edge connectivity less than equal to minimum degree. I have told you na. Now the minimum degree is less than equal to 2e by n floor function. So directly indirectly this thing will be less than this. So I will say that vertex connectivity is less than equal to edge connectivity is less than equal to 2e by n, like this. So from here I can find the upper limit. That is the beauty of mathematics. Like I have, isn't it beautiful? Like I have given you some computers and some wires, and now you can predict very well that I cannot get vertex connectivity or edge connectivity more than this. Like 2e by n, from this formula I can calculate the value. Okay, so let me give you a numerical, you will get more clarity. Take snapshot.
Done, sir.
Okay, so for example, given n and e, what is the upper limit on edge connectivity and vertex connectivity? I have given you the upper limit is 2e by n floor function. Okay, so I think, yeah, so here I have given. Take snapshot.
It is just only to say we don't have any numerics here, no, sir.
Yeah. In the next slide, I will give you some example.
Sir, copy it, sir.
Okay, so see this, n is 10, e is 20. So edge connectivity and vertex connectivity can be at most, they are saying like this. So somebody give you 10 computers and 20 wires, and you will say in return you will say that your edge connectivity, vertex connectivity is less than equal to edge connectivity is less than equal to 2e by n floor function. So 2 into 20 by 10, so you will say 4. So you will say that if somebody attack on 4 edges or somebody attack on four computers, then I cannot guarantee that network will be connected or disconnected. I cannot guarantee that. Okay, that is the beauty. So are you getting it? So they might say that even if 9 computer fail, mine or even if say 7 computer fail, my network should work. So you will say no, I cannot guarantee this. I'm not saying so, mathematics is saying so. That means even if 4 computer fail, I cannot guarantee that the network will work or not. Okay, so if somebody say some you can say some wrong requirements to you, you will immediately say no, it is not possible. Okay, so these are very beautiful concepts. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so next another term is coming, separable. G is separable if and only if G has at least one cut vertex, that is vertex connectivity is 1 and greater than equal to 3 vertices. Okay, so at least one cut vertex means, see, if you want cut vertex, then at least 3 vertices are required. Like if you have only 2 vertices, then none of them is cut vertex.
Yes.
Okay, yeah, so at least 3 vertices are required and vertex connectivity should be 1. Okay, then we will say one cut vertex will be there. Okay, so G is separable if and only if G has at least one cut vertex. This is one way of saying if and only if G has at least one cut vertex. So at least one cut vertex means this only, vertex connectivity 1 and greater than equal to 3 vertices. Okay, so next is G is non-separable if and only if vertex connectivity is greater than equal to 2, that is no cut vertex. If there is no cut vertex, then G is non-separable. Separable is a very simple term. Separable means you can separate it out very easily. I have written it. See this. Separable means we can disconnect it easily. Okay, if you are able to disconnect the graph very easily, it is separable. Non-separable means we cannot disconnect it easily. Easily means you just attack one vertex, game over. Okay, directly indirectly it means one cut vertex. Take snapshot. I will jump to the next slide. Okay, so if question is which of the following graphs are separable, then indirectly they want to ask cut vertex present or not. Okay, if question is which of the following graphs are separable, then indirectly they want to ask cut vertex present or not. Like they can give you some graph and they will say which of the following graph is separable. Okay, so directly indirectly they want to ask cut vertex present or not. This is not separable, this is not separable, this is separable because there is a cut vertex here.
Yes, sir.
Okay, next snapshot. I will jump to the next slide.
Thanks, sir.
Okay, so tree of 3 or more node or 3 or more vertices is separable. Yes, 100% for sure, because every internal node is cut vertex. So if only two nodes are there, then there is no cut vertex. Okay, yeah, cycle graph is non-separable, 100% true. Okay, when we have a cycle graph, it is non-separable because there is no cut vertex.
Okay.
Okay, take snapshot. I will jump to the next slide.
Answer.
Okay, next we are jumping to digraph. Okay, so digraph is of two types: connected and disconnected. Connected means like this, single piece. Roughly, you will say single piece. Disconnected means two pieces, two or more pieces. Okay, if one piece, it is connected. If greater than or equal to two pieces, it is disconnected. Roughly you can visualize like this. Okay, now this connected digraph is of three types. One is weakly connected, unilaterally connected, and strongly connected. Let me give you the definitions of these. Take snapshot.
Answer.
Okay, so what is weakly connected? Underlying undirected graph should be connected. That means one piece. So you just remove the directions and now see graph should be connected. Connected means there exists path between every pair of vertices. Okay, connected means there exists path between every pair of vertices. And here what I am saying, after removing directions. After removing directions. After removing directions. Okay. Yeah, take snapshot. I will jump to the next slide.
Path between every pair of vertices only after removing directions.
After moving directions, yes. After removing directions, there should be a path. Then I will say it is weakly connected.
B to C, we can go. C to D, we don't have a path if it is directed.
Yeah. So that's why I have said, remove the direction and then check. Underlying graph should be connected. So we will get like this, A, B, C, D. So now there is a path within every pair of vertex.
Answer.
Okay, so it is weakly connected. So take snapshot. I will jump to the next slide.
Answer.
Okay. Next is unilaterally connected. Unilaterally connected means a weakly connected is unilaterally connected. That means weakly connected is very, you can say, less restrictive term. Okay, so unilaterally connected is more restricted term. What it is saying, a weakly connected is unilaterally connected if and only if for all x y belong to G there is this path from x to y or y to x. Okay, so see this ABCD is there. So you have to check 6 pair, 4 C2, that means 6. So you will say from between all this. So A to B path is there. Okay, it's okay. A to C path is there. Okay. A to D path is there. Okay. B to C path is there. Okay. B to D path is there. Okay. C to D path is there. Okay. Now that is by chance I have written like this. If I say DC, okay, if I say DC, now D to C there is no path, so no problem. In place of DC you will say CD, check CD. So there should be a path. So you pick every pair of vertices, there should be a path either from A to B or B to A. Are you getting it? If I have taken AB, so there should be path from A to B or B to A, no problem. There should be some path. And what I'm saying, a weakly connected is unilaterally connected. That means if I remove the edges, it should be connected. Okay, now even if directions are there, if I remove the direction, graph should be connected. Now even if I do not remove the direction, then also I will say there is this path from x to y or y to x. That is for sure. Okay,
Awesome.
take snapshot. I will jump to the next slide.
Done, sir.
Okay, next is strongly connected. Strongly connected means a unilaterally connected is strongly connected. Are you getting it? So strongly connected is very strong definition, then unilaterally connected, and then weakly connected. Okay, so what it is saying, a unilaterally connected is strongly connected if and only if for all x y belong to G there is path from x to y and y to x. So everywhere there should be a path. For example, A to B. So how many pairs I have to check? 4 C2, that is 6. So A to B path, yes, there is it is there. Now also check from B to A. Also check from B to A. Yes, there is a path. Okay, it is okay. A to C path is there. C to A also there. Okay. A to D, yeah, we have A to D and D to A also. B to C, C to B also. C to B, yes. B to D, yes, we have a path. And D to B, yes, D to B also. C to D, yes. D to C, yes. So it is strongly connected. Okay, so when can I say graph is strongly connected? So there should be it should be not like that. Okay, for example, this is always outgoing. So So for example, from B to A, there will be no path.
Hmm.
Are you getting it? See this. This is common sense. It's all about common sense. See this. Here we have this like this vertex A. So A always outgoing. There is no incoming. So D to A, for sure there will be no edge. There will be no path. From B to A, no path. C to A, no path, because to A nobody can reach. Okay, so like this, if you have something like all outgoing or all incoming, this all incoming are there. So from D to B, D to C, D to A, no path will be there.
Yeah,
That
the
will create
definition
problem.
says it's like it can be X to Y or Y to X.
Yeah,
Either
yeah.
way.
So, come again.
The path could be either way. If we don't find a path from D to C, we could check for C to D. If
Yeah,
that
yeah, yeah,
satisfies, then.
yeah,
But in
yeah.
a
For you,
strongly connected, we have to have both the ways.
both the ways. Yes, both the ways. So for both the ways, I am telling you this thing, that for both the ways there should be no only outgoing or no incoming, or you can say only incoming but no outgoing. That will create problem. Okay,
In the
so
strong connection.
yeah, in strongly connected. So let me write that point. Okay, yeah, and here itself I have shown you na. See this.
Mhm.
So the only so they are two outgoings and two incoming. So that will create problem. So only incoming create problem. Only incoming or only outgoing, whatever may be the case. Okay, you will say it is not strongly connected.
Yes.
Okay, take snapshot. I will jump to the next slide.
Done, sir.
Okay, so next is walk. So next definition we are starting walk. So it is a list v0 e1 v1 e2 v2 e3 v3 dot 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 ek vk of vertices and edges such that for 1 to k, I is between 1 to k, the edge ei has endpoints vi1 and vi. This is a formal definition. You just apply it, you will get more clarity. Let me apply that. Okay, so this is a graph given to us. This is a graph. So I will say v1 e1 v2 e2 v3. So you just simply check. Walk means what? You simply walk. So v1 e1 v2 e2
E2.
v3. Yeah, this is a walk. Okay, this is a walk. Next, v1 e1 v2 v1 e1 v2 e2. Okay, then v3, then e3, then v4. Okay, then what we are having, e4.
E5.
Okay, and then v5, and then
And
e5 v3. Yeah, this is also a walk like this. So without lifting pen you should do. Without lifting pen you should do. Okay, this is a walk. Next, I have repeated this once again. So I have said here v1 e1 v2 e2 v3. Okay, e3 v4, then e4 v5 e5 v3, then again like this. 2 times I have taken. No problem, you can take here 3 times, 4 times, whatever number of times you want, you can take it. Okay, so what about this? This is important. v1 e2 v3. v1, how you will jump to e2? So v1 e1 v2 e2 v3, like this you should do. So this is not a walk. This is walk, this is walk, this is not a walk. So now see the definition, you get more clarity. It is a list of this vertices and edges such that the edge ei has endpoints vi1 and vi. That means e2 has edge point endpoints. E2 has endpoints v1 and v2. So e2 should have endpoints v1 and e3. So v1 and v3. E2 has endpoints. E2 has endpoints v1 and v3. But here E2 has endpoint v2 and v3. v1 is not the endpoint of E2. So that's why it is not a walk. Okay, so you can say like this also. From v1 you want to jump to e2, so you have to lift the pen and then you will jump here, na? Okay, that is not possible. So without lifting pen, if you are able to do, that is a walk. Very simple. Like you are walking, you are not flying, na? Okay, if you are walking on a road, that means you are simply walking, you are not flying. You cannot fly from one point to another point.
Yes, sir.
Okay, yeah, take snapshot. I will jump to the next slide.
Perfect, sir.
Okay, and here see this, vertices as well as edges can be repeated. There is no problem. Like you are walking on a you can say in park, you are walking on a circular path. You are walking, so you will say okay, I will cover 3 times or 4 times in a park. Okay, so you can cover as many times you want. So like this here, so you can go and come again and again. No problem at all. Okay, so in walk, vertices as well as edges can be repeated. Take snapshot. I will jump to the next slide.
Yes.
Don't worry, I have written that points in the next subsequent slides. You will find the point. Don't worry. Take snapshot.
That's
Okay, so walk from V1 to V3 is called V1 V3 walk. So for example here I will say, so from V1 to V3 we are going, so I will say V1 V3 walk. This is again V1 V3 walk. This is again V1 V3 walk. So walk is not unique. V1 V3 walk is not unique. Okay, this is by
okay.
the way not a walk.
We can
Okay,
have
so
number of circles. That's it.
now see this point. This is important. The what I was saying. Some book says edges can't be repeated in walk, but some says it can be repeated. But vertex can be repeated. That is for sure. Vertex can be repeated. Every book is saying vertex can be repeated. But some books are saying in a walk edges cannot be repeated. But some are saying edge can be repeated. So we are following Nursing Dev book. That is your standard book, and it is saying edges can be repeated. Okay, so no problem. That's why I'm saying that this is also a walk. This is also a walk, but some book will say it is not a walk. So there is a confusion here na? So don't worry, whenever gate exam will ask question, they will properly define what do you mean by walk. Everywhere in every gate question there is no ambiguity at all. So because some books are saying like this, some books are saying like this, so so in gate exam if they want to ask any question regarding walk, they will properly first define that. That means in walk, directly indirectly you will come to know up from the definition that they are saying that this can be repeated or not. Vertex can be repeated for sure, but edges repetition is a confusion. Edges can be repeated or not. So for that
I,
they will
I
clarify
didn't
that.
get, I didn't get like how vertex are being repeated, not the edges. We have to walk over the edge to reach the edge, to reach the other vertex, no, sir?
Vertex, okay, okay, so it's just about imagination.
Huh.
A B C D E. So now go A C E D C B A. You have repeated the vertex, but no edge is
Yes.
repeated.
Yes.
Okay, A C E D C B A.
Understood, sir.
Okay, okay. So yeah, yes. So next, what they are saying, if edges are not labeled, then walk is sequence of vertices such that between two successive vertices there is an edge. Like in previous example, we can say V1, V2, V3, or V1, V2, V3, V4, V5, V3, and so on. Okay, V1, V3, V5 is not a walk. You can check that out. V1, V2, V3. So I have labeled here edges. Now, if edges are not labeled, you will simply say V1, V2, V3. It is a walk. Or you will say V1, V2, V3, V4, V5, V3. Or if say V1, V2, V3, V4, V5, V3, V4, V5, V3, V4, V5, whatever number of time you can say, you can take that. Okay, but condition is that V1, V2, V3. Why it is a walk? Because V1, V2, there should be an edge. V2, V3, there should be an edge like this. Is it okay?
Huh, sir.
Okay, yeah. So that's it. And V1, V3, V5. Why it is not like that? So V1, V3. So from V1 to V3, how you have jumped that? Where is V2? Okay, that's why it is not a walk. Take snapshot. I will jump to the next slide.
Okay, sir.
Okay. So walk can be of two types: open walk and close walk. Open means start and end not same, like this V1, V2, V3. Close means start and end are same, like V3, V4, V5, V3, V4, V5, V3. I have done here mistake. V3, V3, V4, V5, V3 na. V3, V4, V5, V3. V3, V4, V5, V3. Okay, so this is a close walk means simply start and end are same, like loop.
Huh,
Start
sir.
and end is same. Okay, yeah, open means start and end are different. Okay, walk is just like tracing a graph with pen, and pen does not get up. I have told you na, without lifting the pen. So here
Yes, sir.
also your doubt has been removed na, like vertices are repeated. See this.
Huh, sir.
Okay. So take snapshot. I will jump to the next slide.
Done.
What is a trail? So some books are saying trail and walk are same, but Nursing Dev book is different. It is saying that in walk vertices and edges can be repeated, but in trail vertices can be repeated but edges cannot be repeated. So same is, see this, what they are saying, walk with no repeated edge. Okay, hence vertex may be repeated but edge cannot be repeated. So some authors are saying trail as walk, some are saying trail and walk are same, but no, they are actually not same. Your Nursing Dev standard book is saying like that. I'm not saying, your book is saying. That's why we are taking it as different. So walk is walk with no repeated edge. Okay, so trail implies walk one way theorem. Obviously, when we have a trail, it will be a walk, but when we have a walk, it may or may not be trail. For example, this can be repeated. Okay, so see this in the previous example, 1 and 2 are trail from v1 to v3, hence it may or may not be unique. Okay, it may or may not be unique, no problem. So for example, see this 1 and 2, 1 and 2 were trail because no edges were repeated. Okay, see this v1 v2 v3 and v1 v2 v3 v4 v5 v3, no edges repeated here, no problem. Okay, so they are you can say trail.
Right.
Okay, yeah, two trails from v1 v3 trail, and they may or may not be unique. So here they are not unique. Okay,
Mm.
yeah.
But example 3, it's not a trail, so it is a
Ha,
path.
yeah, yeah, yes, good. I was just about to say that in the slide I have shown you. So this
Oh.
is not a trail, but it is a walk. Okay,
Mm.
yeah.
Yes.
So I have written here. So 1 and 2 are trail from v1 to
Ah,
v3, hence it may or may not be unique. Similar to walk, trail can be open or closed. Okay, so I have not written that. Don't worry. So let me write it here. 3 is walk,
oh, but not trail.
but not trail. Okay, yeah, similar to walk, trail can be open and close. Okay, no problem.
Yes, sir.
Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so what is a path? So now path is a different term. So see this, I have written here clearly. So vertices and edges. In walk, both can be repeated. In trail, vertices can be repeated, but edges cannot be repeated. In path, nothing can be repeated. Neither vertices nor edges. Okay, path means nothing can be repeated. So see this, path is a trail. So as soon as I say trail, you will say okay, no edge repeated. No edge repeated. Okay, so path is a trail in which no vertex is repeated. Path is a trail in which no vertex is repeated. So in path, neither vertices nor edges can be repeated. Not self-intersecting trail is a path. So for example, this is a path like this. Okay, but this is a trail. It is not a path. Why? Because it is self-intersecting. Na? It is
Mm.
self-intersecting. It is cutting itself. So it is a trail, but it is not a path. But path will be like this. It cannot be self-intersecting. Self-intersecting means you can say
Linking it.
vertices are repeated.
Yes, sir.
Vertices will be repeated. Take snapshot. I will jump to the next slide.
Done, sir.
Okay. So every path is trail and hence walk also. So I think you have got it. Path, trail, and walk. Okay. It is very less restrictive. There is a restriction that edges cannot be repeated. There is a restriction that vertices and edges both cannot be repeated.
Yes.
Take snapshot. I will jump to the next slide.
Okay.
Okay, so similar to trail and walk, path can be either open or close. Open means start and end vertex are not same. No vertex is repeated like v1, v2, v3. It is it is a path. v1, v2, v3 is a path. See this. v1, v2, v3 is a path. Okay. Yes. So close means obviously start and end vertex must be same. Okay, so in path, vertex can't be repeated except first and last. If first and last are same, then it is a closed path or circuit or loop or cycle or polygon. These are the different names for the closed path. What is the different name of closed path? Circuit, loop, cycle or polygon. Okay, so like v3, v4, v5, v3, that is a closed path. You can check that out. v3, v4, v5, v3.
Done, sir.
v3, v4, v5, v3. Triangle. Okay, this is
Okay.
a closed path. Okay, take snapshot. I will jump to the next slide.
Done, sir.
Next, length of path, walk or trail is number of edges in it. That is very simple. What is length of path or walk or trail? Number of edges in it. Like v1, v2, v3, length. So 1, 2. So 2. Okay. So here 1, 2, 3. So it is 3. v3, v4, v5, v3. v3, v4, v5, v3. You can check that out. v3, v4, v5, v3. So 3. 3 is the answer. Okay. Yeah. So it is very easy now. v1, then e1, then v2, then e2, then v3. So number of vertices minus 1 is the answer. Very, very simple. V minus 1 is the answer. So here 2, here 3. Any doubt?
Yes, sir. Like when it is open, when it is closed,
Yeah.
it is V.
If it is closed, no. 4 vertices are there. Still it is 3, na? V
Yes,
minus
sir.
1 is the answer.
Done.
Okay, take snapshot. I will jump to the next slide. Done.
Done.
Okay, next, cycle of length 1 is self loop like this. So this is a self loop, na? So AA, we will write it like AA. Cycle of length 2 is parallel edges like ABA. Cycle of length 3 is triangle like this ABCA. Cycle of length 4 is like square or rectangle, whatever way you want. So that's why we are calling it as a polygon type. See, these are polygons, na? That's why. Okay, so cycle of length 1, cycle of length 2. Cycle means closed path, na? Okay,
Yes,
so from A to A, okay, self loop. From A B A like this, we will say A B A. That is a closed path, na? Okay, so parallel edges. So length 3, length, I think you have got it, na? Length, number of edges in it. So number of edges, see. Okay, so length is 1, number of edges only 1. Okay, length 2 because number of edges are 2. A B A like this. Okay, A B C A. So 3 and 4. Any doubt here?
No, sir.
Okay, take snapshot. I will jump to the next slide.
Okay, sir.
Next is girth of graph. Girth means length of the smallest cycle or circuit in the graph. So what is the girth? Smallest cycle, 3 lengths, 3, 4, 3, 1, 2. Here, infinite. Okay, because there is no cycle. Okay, so hence in simple graph, minimum girth is 3. So if we have a simple graph, minimum girth will be 3 only. In pseudo graph, girth can be 1. In multigraph, girth can be 2 also. Any doubt here?
In pseudograph, like why it is 1, sir?
Because self loop. See this?
The length
Cycle of length 1 is self loop. So I have said na length of the smallest cycle or circuit in the graph. Smallest. So smallest is self loop here. So that's why 1. Here parallel edges. That's why 2. So in simple graph, minimum girth will be 3 because neither parallel edges nor self loops are allowed.
Yes, sir.
Okay, and here it is infinite. Why infinite? Because there is no cycle at all.
Yes, sir.
Take snapshot. I will jump to the next slide.
Okay, sir.
Okay, so now we are going to start another very important topic. Many times question have been asked. It is Euler graph. Okay, somebody calls them as Euler. It is not Euler. It is Euler. Okay, we should pronounce this properly. Euler. So it's name of the scientist. So we should pronounce this properly. Okay, otherwise he will feel bad that why my name is not pronounced properly. Okay, yeah. So it is Euler. So a graph is Euler if and only if it has at least one Euler cycle or circuit. And by the way, this is very brilliant scientist, and I think 72 mathematical objects he has invented. So he's a very brilliant scientist. Okay, so we should respect him, and we should pronounce his name very properly. Euler. So graph is Euler if and only if it has at least one Euler cycle or circuit. Okay, so Euler cycle is closed trail which include every edge of the graph. Okay, so I can say like this also. Euler cycle is a closed walk which include every edge of the graph exactly once. Trail means what? In trail is a walk in which no edge is repeated. So that's why I have written Euler cycle is a closed walk which include every edge of the graph exactly once. So now you may argue with me, sir, you have used the word cycle or circuit. See this, you have told that cycle or circuit is a closed path. Closed path is cycle or circuit, na? But here you are saying it is walk or trail. How is it so? It is an exception because Euler has invented it when graph theory was just begun. So at that time they were scientists did not care about what he is saying and all. So that's why, and just as a mark of respect, they have not changed the name. Okay, so they should say Euler trail. Okay, but still they are saying Euler cycle just because as a mark of respect to him. Okay, so cycles, I have written this point clearly. See this, cycle is a closed path and not closed trail, but Euler cycle is an exception. Okay, Euler cycle is an exception. So Euler cycle is a See this Euler cycle is a closed trail which include every edge of the graph. Okay,
Yes, sir.
so take snapshot. I will jump to the next slide.
Done, sir.
Okay. So what is the
Just-
simplest way? Okay, take it.
Yeah, sir. Yes, sir.
Okay, so what is the simplest way to define Euler graph? Simplest way is a graph is Euler if and only if it has a closed trail connecting all the edges. Okay, so you have to traverse all the edges of the graph, and in such a way that vertices may be repeated, but edges can never be repeated. Okay, and you have to go to each and every edge. So roughly I will say go to each and every edge of graph, but edge can't vertices can be repeated. Vertices can be repeated, but edges can't. That is the simplest way to define. Okay, for example this. So you will start from a cover this edge 1 2 3 4 and you come back from where you started. Okay, go to each and every edge of the graph. Vertices can be repeated but edges can't, and start and end same. Start and end same vertex. That is Euler. Okay, so start from a you have visited all the edges and come back to the same vertex. That is Euler. So here main concentration is on edges. So all the edges should be covered. That is the basic thing. Okay, so start from here and you cover all of them and come back again. All edges should be covered. Okay, yeah, take snapshot. I will jump to the next slide. Okay, so is it Euler? So I will try to do it. So what I will say, so yeah, start from here 1 2 like this. Yeah, it is Euler. Okay, what about this? You can start from anywhere. So you start from here, this like this, everything covered, but this edge is not yet covered. So the moment you covered it, so you started somewhere but you ended it here, so it is not Euler.
Okay. Yes.
Okay, and it is very obvious also. See this. Degree of this vertex is 1 2 3 4 and 5 degree. So if it has 4 degree, then I will say very easily, like you from some path you come here, you go out, then again you come here and go out. So even degree is sufficient, must. But here we have odd degree. So odd degree means 1 2 3 4 5. So you come from here, you go out. Then from some other way, you come here, you go out. Now what about this? That will create problem. Okay, that is the intuition idea, rather intuitive idea. Okay, so what about this? Now you will simply say 1 2 3 4 5. 5 gone. No, it is not Euler.
Done, sir.
Okay, yeah. Take snapshot. I will jump to the next slide. Okay, so multigraph can be Euler also, and these are nothing but multigraph only. Okay, these are multigraph. Na? Parallel edges are there, so no problem. Multigraph can be Euler also, and graph may have more than one Euler circuit also. Okay, we can have more than one Euler circuit also. So like this, you have covered like this, or you can cover from here also. Okay, so multiple circuits are there. Don't need to worry. So graph may have more than one Euler circuit also, and multigraph can be Euler also. Take snapshot. I will jump to the next slide. Okay, so a very beautiful theorem is coming. Euler graph means every vertex has even degree. So if graph is Euler, then every vertex should be of even degree. That is for sure. I have just proved you. Okay, proof I have just given you in the previous slide. So like 4. So you come from here, you go out. You come here, you go out. But what if odd? If odd is there, you go out. Okay, first you come and go out. Come, go out. Then come, go out. What about this? Okay, so if graph is Euler, then every vertex has even degree. And see this properly. In logic style I have written that so that you get more clarity. One way theorem.
Yes, sir.
Okay, so if every vertex is of even degree, like P imply this is P and this is Q. Q implies P. Q implies P will be false. That means every vertex is of even degree, then it is Euler. Simplest example, see this: A, B, C, D, E, F, and G. What about this scenario? So you start from here. You now how you will reach here? That is not possible. Okay, and every vertex is of even degree. Even then, it is not Euler. So clearly, it is false. Okay, so it is one-way theorem that if graph is Euler, then every vertex has even degree. So now take the contrapositive. Contrapositive means what? Not Q implies not P, and you know direct. This is direct, na? P implies Q direct. Okay, Q implies P is converse. Inverse is not P implies not Q. This and this are equivalent. These and this are equivalent. So contrapositive I have used. So not Q implies not P. That means if every vertex is not of even degree, then for sure it is not Euler.
Yes.
Okay, I have used this here.
Sir.
So contrapositive I have used. So not even implies not Euler. Shortly I have written. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so Euler implies connected. So this is a question. That means every Euler graph should be connected. Now, like this, I have shown you this is a disconnected graph. So it was not Euler. So can I say like this? Every Euler graph is connected? No. This is the simplest example. See this: A, B, C, and D. So you start from C. So you will say C, A, B, C. That's it. You have covered all the edges. And from where you started, you come back. I have not said about vertices. You have to cover all the vertices in Euler. Okay,
That's
so
it.
all the edges are covered. That's it. So Euler implies connected. No, it is wrong. Okay, this is an Euler graph. Take snapshot. I will jump to the next slide.
Yes, sir.
True, false. Graph is Euler if and only if every vertex is of even degree. If and only if means both ways. So graph is Euler, every vertex is of even degree. I have told you. But if every vertex is of even degree, graph is Euler. No. So this is false. Are you getting it now? If and only if means both ways.
Sir.
Graph is Euler if and only if every vertex is of even degree and it is connected. So both ways you have to check. So graph is Euler, then every vertex is of even degree and it is connected. This is even this is false. Okay, so if graph is Euler, then every vertex is of even degree and it is connected. No. This is see this.
The previous example.
Okay.
Yes, sir.
Yeah. Okay, so this is wrong. Next, graph is Euler if and only if every vertex is of even degree and at most one non-trivial connected component. This is very, very important. Make some star. This question has not yet come in GATE exam, but someday it will definitely come. This is very, very important. This is true statement. What they are saying is, so directly, indirectly, see this. What they are saying, one non-trivial connected component. Connected component we have studied in the previous lectures only. So non-trivial means, trivial means this only single vertex. Non-trivial means like this. At least two vertices are there and one edge is there. So if we have like this, and we have a like triangle and this, so it is not Euler. For sure it is not Euler. Why? You will never reach this even edge. From here you will never reach this even. So all edges are not covered. I have told you in Euler our main concentration is on edges. All the edges should be covered. So you will not be able to cover those edges. So that's why it is correct statement. Are you getting it? At most one non-trivial connected component. Okay, so like a zero at most one non-trivial connected component, na? So zero non-trivial connected component is also allowed. That means all are trivial connected components. So like this is for sure Euler. It is 5-4. Why? Because I will say from this A, I have started from A and I have come back to A, covering all the edges. See carefully, see my statement. I am saying I have started from A and come back to A, covering all the edges. So you may say, sir, no, you are not saying true statement, you are false. Then you will say, then I will say, okay, if I am false, then please give me my edge. Where is an edge? Okay, which is not covered. Yeah. So that is the way you can check. So it is trivially, no problem. It is Euler. Okay. So so this is very beautiful statement. Graph is Euler if and only if every vertex is of even degree and at most one non-trivial connected component. Okay. So this is also Euler. Okay, no problem. A, B, C, and rest all are trivial components. No problem. Okay. Yeah. So overall in this graph, at most one non-trivial connected component. So rather I should say exactly one non-trivial connected component. Rest others are trivial. So no problem. So that's why I have said na ki at most one non-trivial connected component should be there. Okay. And every vertex is of even degree, that is for sure. Next, a connected graph is Euler. This is your Nursing Dev statement, book statement. They can ask Nursing Dev book. So what they are saying, a connected graph is Euler if and only if every vertex is of even degree. They are saying that we have a connected graph. So now directly indirectly they are saying at most one non-trivial connected component. They have said so. Okay, so they are saying we have a connected graph. So connected graph is Euler if and only if every vertex is of even degree. So you have to prove like this also. You have to prove like this also. Right? So I will say if graph is connected, then every a connected graph is Euler implies every vertex is of even degree. Yes, this is for sure, and this is also sure. Every vertex is of even degree, then a connected graph is Euler. Yes, that is for sure. Okay, so this is also true. So C and D are true, A and B are false. So if you want to explain something else, so then I can explain. Otherwise, I will jump to the next slide.
B point, sir.
Key point. Okay.
Because
So what they are saying is we have already a connected graph. So now our see these are the set of graph in this universe, all the graphs. So now I am concentrating only a subset of it, that is connected graphs. Okay,
yes, sir.
I am not talking about disconnected graphs. So directly indirectly we have got the point. Like in a connected graph, if every vertex is of even degree, it will be Euler only.
Yes, sir.
Okay, like this you take like this.
Yes, sir.
So if we have a connected graph and every vertex is of even degree, for sure it will be Euler. Like this you can say na, this is a vertex, so one incoming then outgoing, then incoming then outgoing, so no problem. Okay,
Yes, sir.
take snapshot. I will jump to the next slide.
Done, sir.
Okay, so these are some examples. So null graph, I have already told you, it is always Euler. Like this, a single vertex, two vertices, three vertices, four vertices, and so on. Whatever you want, you can take 5, 1, 5, 2, 5, 3, 5, 4, everywhere. Okay, K regular is connected and K is even. So I will say if we have a K regular graph like 2 regular, 3 regular, 4 regular, and so on, so it will be Euler when we will say it is a connected and K is even. Okay, so because we want every vertex to be even degree na, and it should be connected also, then it will be Euler. Kn when n is odd, because when n is odd like K3, okay, like K5, so it will be what, 2 regular, it will be what, 4 regular. So every vertex is of 4 degree here, every vertex is of 2 degree here, so even degree Euler, that is for sure. And Kn is always connected, so no need to worry. Okay, so Kn when n is odd, it is Euler. Okay, so K1 is also, K1 is your 5, 1, it is also Euler, don't worry. Cn is always Euler. Why? Because cycle graph of C3 is the smallest, C4, C5, it is always Euler because it is 2 regular and connected. Okay, Cn is 2 regular and connected, 2 regular and connected. So two regular means every vertex of even degree, so it will be Euler, and because it is connected also, so no need to worry. Okay, next is Qn. When n is even, it will be Euler. Qn, so when n is even like Q2, Q4, and so on. Okay, because Q3, I think you already know na, Qn is n regular. I have told you na, Q3 was Q, it was 3 regular. So 3 regular means every vertex is of 3 degree. So every vertex of 3 degree, then obviously it is not Euler. Okay, so when n is even, it will be Euler. Wn, wheel graph, it is never Euler. That's why I have closed. Why it is never Euler? Because see how we have made the wheel graph. C3 we have taken, and then we have connected it. So every vertex of degree 3, that means odd degree, so it will create problem. Again see this, so this is of 4 degree, but every other vertex is of degree 3. So are you getting it? So degree 3 vertices will create problem. Like again you can take pentagon. Now you try to make wheel graph. So these vertices are of degree 3. That will everywhere create problem. So Wn is never Euler. Bipartite I have given question mark because it entirely depends. Okay, so we can make connected also, disconnected also. Bipartite can be any way like this. So that is this okay, so yeah, this is not Euler because we have degree 1, two vertices of degree 1, so it is never Euler. So for example A B C, so start from A B C. So now from how you will get come back to A again? You can never come back to A again. Okay, so A is of degree 1 and C is also of degree 1, but I have told you every vertex should be of even degree, only then it is Euler. Okay, so like this, if I join it like this, yeah, then it is Euler for sure. A B C D A. Are you getting it? A B C D A. So bipartite can be Euler, not Euler, it hardly matters. KMN, when M and N are even, then it will be Euler for sure. M and N are even. See this. Here we have M vertices, here we have N vertices. If both are even, so so every vertex here will have what degree? N. Every vertex will be of N degree. If N is even, so directly indirectly every vertex is of N degree. And here, so that means even degree. And here every vertex is having M degree. So M degree means if M is even, then here also every vertex will be of even degree. So every vertex is of even degree, for sure it will be Euler. So that's why we are saying KMN, MNN should be even.
Even.
Yeah, take snapshot. I will jump to the next slide. Okay. So next is unicursal graph. What is unicursal graph? G is unicursal if and only if there exists open trail which include every edge of the graph. So there exists a open trail. Okay, open trail means it is not close. That means start and end not same. Start and not same. Okay, so yeah, so this open trail is known as Euler path or Euler trail or unicursal line. Okay, this open trail is known as Euler path or Euler trail or unicursal line. These are the just terminology. Take snapshot. I will jump to the next slide and I will show you examples. Done.
Answer.
So see this, I have properly highlighted it. So these are the two vertices of odd degree. So you will start from here, like this. You will go, you will cover all of them, and then again come here. So start from here, you will come through here. Okay, so this is an open. It is not closed now, because from here how you will come back to here. So same is the case here. So A and B. So you start from here like this. You go. Okay, open. So now here it is not. So for example, you start from here, here. So whatever this, you cannot cover it. Okay. Yeah.
First and second are correct.
Yeah, first and second are correct. Third is not correct. Done.
Done, sir.
So in case of Euler trail, if we have an edge between initial and final vertex, we get a Euler circuit. That is very simple. So now if we draw an edge from here to here again, so now you were here now, so from this edge you will come here. Okay, so you will get a Euler circuit. Okay, your graph will become Euler. Okay, so unicursal graph will become Euler when we have an edge from the first and the last vertex. And this is for sure for unicursal. So okay, so let me see that I have written theorem here or not. Yeah, I have written. Okay, so this point I will explain after this point. So I have written here, see this, a connected graph is Euler if and only if we have exactly two vertices of odd degree. Okay, there should be exactly two vertices of odd degree. So for example, see this, this is a vertex of degree 3. So from here you will come in, from here you will come out, and then again you come in. So there is no way to go out. Okay, so for example, you can take another way. So here you go out, you come in, and here you go out. Then no way to come in. That is the problem. Okay, so and we have another vertex of degree odd. So we will say, so you go out, so you come in here, okay, and then from somewhere you come here in, and you go out. So now from here, if you go out and here, let us suppose you come in. So directly and directly what I want to say, so no need to go into more complex things. I simply want to say that if we have a unicursal graph, in unicursal graph we will have exactly two vertices of odd degree, and you have to start from these odd degree vertices only. So for example, see this A, B, C and D. So you have to start from A or you have to start from C. If you start from B, then you won't be able to find a cycle. Okay, so for example, you start from B. So let me say B to A to D to C to A. This edge is not yet covered. Are you getting it? So another way, B to C, C to D, D to A to B. Then how this edge will be covered? So no way out. So directly and directly what I want to say is, in unicursal graph there will be exactly two vertices of odd degree, and to cover all the edges you have to start from odd degree vertex only. So directly and directly in unicursal graph, start and end vertex will be odd degree vertices. So you have to start from here, end will be C, or you start from C, end will be A. That is for sure.
Yes.
Okay, yeah, so that's why I have told that these are the odd degree vertices. So now even if you have one more edge, so directly and directly all will be of even degree, and the moment we have all vertices of even degree, then graph will be Euler. Are you getting it now? So that's yeah, any doubt here?
No, sir.
Okay, so that's why now read this point, you will get more clarity. In case of Euler trail, if we have an edge between initial and final vertex, we get a Euler circuit.
Yes, sir.
Take snapshot, I will jump to the next slide.
Done, sir.
Okay, traceable graph. Traceable graph means number of odd degree vertices are 0 or 2. That means traceable if and only if graph is Euler or unicursal. That means without lifting pen you can guess that. Okay, I think I have just a second. Yes, so now let me see. A traceable graph means number of odd degree vertices are 0, 2. That means we will say graph is traceable if and only if graph is either Euler or unicursal. That means without lifting pen you can make it. Without lifting pen you can make diagram. You can make graph. If without lifting pen you can make the graph, it is traceable graph. Traceable means you can trace it. Trace it without lifting the pen. Okay, so it will be traceable if and only if number of odd degree vertices are 0, 2. That means graph is either Euler or unicursal. 0 means Euler, 2 means unicursal. Odd degree vertices. Is it okay now? So so this is traceable or not? Yes. So you here. So number of odd degree vertices are 0 here. 0 means Euler. Euler is traceable. This number of odd degree vertices are 0. Okay, so like this you can easily trace it. Okay, so it is traceable, and they are Euler also. What about this? Okay, yeah, now see this. So now number of vertices of odd degree are 2 here, so it is traceable and it is unicursal. Okay,
So you made
so
a line inside there?
yeah, I have made the line inside. I have in the figure I have I was not able to copy that. Yeah, this is the graph. Okay, so what I will say, this is Euler, this is Euler, this is unicursal. So all these are traceable graph, and this number of odd degree vertices are 4, so it is not traceable. Not traceable means without lifting pen you can never make this. Okay, so I think in your childhood you have studied that, try to make
I
this.
just thought of those things.
Yeah, so we cannot make it, and now you have got the proof that why we cannot make it. This is the formal proof that why we cannot make it, because number of odd degree vertices are here 4. So if odd degree vertices are 4, then from how you will come back, na? So that means incoming outgoing proper, so there should be one outgoing and there should be no incoming. So for all the four, this is the same scenario. Okay, so directly indirectly from here I will reach here, but this edge will never be covered. Are you getting it? See this, when you try to make it, you were able to draw this, but this edge you can never make it, na? Because this is unicursal, this is unicursal till this is unicursal. Okay, so you start from here, you come here, but now this you will never be able to cover it. Okay, yeah. Take the snapshot. I will jump to the next slide. Okay, so yeah, okay. A slide was duplicated. Okay, next is Hamiltonian graph. This is also very important. Many times question have been asked. So G is Hamiltonian if and only if there is a Hamiltonian cycle or circuit in it. Okay, yeah. So actually someone is calling, so just wait for 1 minute. I'm just coming. Okay, I'm just coming. Okay, so what we were studying, Hamiltonian graphs. Yeah, are you there?
Sir.
Okay, so G is Hamiltonian if and only if there is a Hamiltonian cycle or circuit in it. So what is Hamiltonian cycle? I have explained it here. So Hamiltonian cycle is a closed path. See the cycle means closed path. I have told you. So now in Hamiltonian there is no exception. In Euler there was exception. Okay, so Hamiltonian cycle is a closed path. Cycle means closed path only. So no need to worry. Closed path which include every vertex exactly once except first and last. So path means every vertex should be covered. Okay, so that's why I have told you every vertex should be covered and exactly once. Path means no repetition. Path means no repetition of vertices. So but here exception is that this is a special path which will cover every vertex exactly once. Okay, except first and last, obviously because it is a close, so first and last will be repeated. Okay, now since it's a path, so no vertex or edges can be repeated, but Euler cycle was closed trail in which vertices can be repeated but edges cannot be repeated. This is very important point. Okay, in Euler vertices were repeated na, A, B, C, D. So we have told you vertex can be repeated but edges can never be repeated. And in Euler, main concentration was on edges. You have to cover all the edges. In Hamiltonian, main concentration is on vertices. They are saying every vertex should be covered exactly once. Okay.
Does it mean that we should not retrace it? So
Retrace.
Every vertex to be covered at least once means
Exactly once. Exactly once. Self-intersecting not allowed. Okay, so like this. This is this Hamiltonian A B C D. Yeah, A B C D. Just we have covered all the vertices exactly once, so it is Hamiltonian.
No matter whether we don't go from D to B and A to C.
No. Edges. There is no nothing given for edges. See this. Hamiltonian cycle is a closed path which include every vertex exactly once, except first and every vertex. Okay. So here Hamiltonian in Euler main concentration was on edges. That means every edge should be covered exactly once. In Hamiltonian main concentration is on vertices. That means every vertex should be covered exactly once. Okay, take snapshot. I will jump to the next slide.
Done, sir.
Okay. So in Hamiltonian, main concentration I have written here. In Hamiltonian, main concentration is on vertices, but in Euler, main concentration was on edges. Okay. So hence in Hamiltonian, no need to cover every edge. That means edges can be skipped, but we have to cover every vertex. Okay. So in Euler, vertices can be skipped, no problem. We have to cover all the edges. But in Hamiltonian, edges can be skipped, but we have to cover every vertex. Okay, so acyclic or disconnected graph are never Hamiltonian, that is for sure. If graph is acyclic or it is disconnected, it is never Hamiltonian. Why? If graph is disconnected, then you will not be able to reach this vertex. Okay, and our main aim is to cover all the vertices.
Understood, sir.
Okay, take snapshot. I will jump to the next slide. Okay, so we will now check this. This is very simple, A, B, C, D. So you start from here, you come back. That's it. This is Hamiltonian. Very, very easy. So is this Hamiltonian? So you start from here. A, B is like this. You go, go, go. Now how you will come back? You have to repeat it. It is not.
Oh, we can't stop without tracing the edge, sir? Because all the vertices got over, no?
How all vertices are go over? Start and end should be same, na?
Yes. Yes, sir.
Okay. Start and end should be same. So we have to come back. But if I want to come back, this will be repeated. That will create problem. So for GATE exam, you can think like that. So we have a body of a human, and this is the neck part. If you have a neck like this, it is never Hamiltonian.
Yes, sir.
Okay, that will create problem. So here, is it Hamiltonian? So let me check that out. So these are the vertices. So from here, I will start here. But I have repeated somewhere. Okay, so let me do it again. So here, you come back here. Yeah, it is Hamiltonian. Have you got it?
Yes, sir.
Okay, so I just go out. So from here, I go out and then come back. Okay, so this is Hamiltonian. And by the way, this is nothing but your cube only. Okay, so try to focus. Cube is also Hamiltonian. Okay, I have just compressed the cube and I will get it.
Yes, sir.
Take snapshot. I will jump to the next slide.
That's
Peterson graph. So this is question of GATE 2022. Peterson graph is Hamiltonian or not? So you have to try it out yourself. There is no proper way out to check Hamiltonian. For Euler, there was very simple way out. Every vertex of even degree and connected. If graph is connected and even degree, every vertex of even degree, by default you will say it is Euler. No need to check. Okay, but here there is no shortcut like that. Anyway, it is an open problem, $1 million problem. So if somebody solve it, that person will get $1 million. Okay, open problem means nobody have proved that we cannot have necessary and sufficient condition for this Hamiltonian graphs. Okay, necessary and sufficient. This is necessary as well as sufficient. Na? Necessary means this condition false, then it is not Euler. Sufficient means if this condition true, then it should be Euler. I think I have told you necessary and sufficient. Sufficient means yes to yes, no, then we do not know. Sufficient and necessary means no, then no. For yes, I do not know. How to get? Do you know this thing? No? Sufficient, yes, and for necessary, yes, we do not know. No, then it is no. So it is necessary as well as sufficient condition, because yes to yes, no to no. Okay, so till now nobody is able to find a necessary as well as sufficient condition for Hamiltonian graphs. So if in say 10 year, 20 year or 100 years down the line somebody can find that out, then he or she will get $100 million. Or even if somebody prove somehow that there is no necessary and sufficient condition, then also you will get $1 million. Okay, so this is an open problem. Open problem means no information. Till now there is no information that there is necessary or sufficient condition or not. Okay, if there is a necessary and sufficient condition, then you have to find that out, or you have to prove that there is no necessary and sufficient condition. So nobody is able to prove both the things. Neither somebody is able to prove that there is no necessary and sufficient condition, and neither somebody is able to give us necessary and sufficient condition. So now, since nobody has proved that there is no necessary and sufficient condition, so we have to imagine that there might be some necessary and sufficient condition for it. Are you getting it now?
Mm-hmm.
Okay,
Yes,
so that is an open problem. So only ways you have to do hit and trial. Okay, so like this, you go like this, and you try to come in. Okay, and now if you go, so now you have to repeat the vertex. So anyway,
yes.
you just try it out. The more you try, the more you get. It is not Hamiltonian. I have just given you the idea. It is not Hamiltonian. So try to do all the paths and all. Okay, try to explore it. Take snapshot. I will jump to the next slide.
Done, sir.
So Hamiltonian path is an open path which include every vertex of the graph, every vertex exactly once. Next definition is Hamiltonian path. Previous was Hamiltonian circuit or cycle. See this, we have done Hamiltonian cycle. So when can I say graph is Hamiltonian? When there is Hamiltonian cycle or circuit. Hamiltonian graph means Hamiltonian cycle or circuit we have to find. But now I am showing you another definition, that is Hamiltonian path. So Hamiltonian path is an open path. See this, it is an open path which include every vertex exactly once. So it is very trivial definition actually. So A B C D like this. So you will say A B C D, you take. So you just delete the last vertex, like this is Hamiltonian graph, na? Because we will say A B C D A like this. So you just delete this A and you will get what? An open path, A B C D.
Yes, sir.
Okay, so that is trivial thing. It is not so, you can say, important and all. It is trivial, anybody can think of it. So delete last vertex in Hamiltonian circuit, we get Hamiltonian path. That's it. Okay,
Yes, sir.
take snapshot. I will jump to the next slide.
Done, sir.
Okay, so I have written it here. No necessary and sufficient condition for graph to be Hamiltonian, unlike Euler. For Euler we have, but here we do not have. Okay, so but still we have few one-way theorems. So first is pendant edge theorem, then Dirac's theorem, then Or's theorem, then simple graph with n minus 1 plus c2 edges is Hamiltonian. One by one we will study these four theorems. Take snapshot. I will jump to the next slide. So these theorems will help you in GATE exam to check whether graph is Hamiltonian or not. Rather, they are very complex theorems actually. I will just tell you what are these theorems. So no need to apply these theorems, just for the sake of you can say completion. I am telling you, and MSQs are coming in GATE, so they will directly ask these as true or false statement. So you should know these statements, and anyway, Or's theorem, this has been asked in GATE directly they have asked this. Okay, so it's better you should know these theorems. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so first is pendant edge theorem. So if graph is if we have a Hamiltonian circuit, that means graph is Hamiltonian, then there should be no pendant edge. Pendant edge means degree 1. Degree 1 vertex. So like this is a pendant edge. Okay, so obviously when we have a pendant edge, then for example you start from A, how you will come back to A? If you reach E, there is no way out to reach back to A. Okay, so from E, if you draw an edge from E, if you draw edge to A, then there is no pendant edge anywhere because there is no pendant vertex. Okay, are you getting it now?
Yes, I understood, sir.
Okay, so again see this, there are two pendant edges. Yeah, it is not Hamiltonian. Again, two pendant edges, not Hamiltonian. Okay, so hence as soon as you see pendant edge, immediately say not Hamiltonian graph. Okay, so what is the pendant edge? Pendant edge means degree 1 vertex, the edge to the degree 1 vertex. That is pendant edge. Take snapshot. I will jump to the next slide. Okay, so yeah, so I have told you this is one-way theorem, na? So Hamiltonian circuit implies no pendant edge. So one-way theorem means converse is not true. That means no pendant edge means Hamiltonian circuit. No, see this, I have told you, no pendant edge and still not Hamiltonian. There is no pendant edge and it is not Hamiltonian. I think you have got it. So start from A. Okay, so you go here. Now you have to come back, but there is no way out. Okay, yeah, so there is no pendant edge and still it is not Hamiltonian. So this is one-way theorem. That means Hamiltonian circuit implies no pendant edge. So if graph is Hamiltonian, there is no pendant edge. But converse is not true. That if there is no pendant edge, you will say graph is Hamiltonian. No. Okay, this is the example. Take snapshot. I will jump to the next slide.
Done, sir.
Next is direct theorem. Direct theorem is saying let G be a simple graph of order greater than equal to 3. For all u belong to G, degree u should be greater than equal to n minus 2 implies G is Hamiltonian. That means if every vertex has degree greater than or equal to n by 2, graph will be Hamiltonian, where n is order of the graph. Okay, let G be graph of order greater than equal to 3. So where n is the order or number of vertices, n is the number of vertices. Okay, for example, this graph, I will say degree u is greater than equal to 4 by 2. So degree u is greater than equal to 2 for all u. For all the vertices, you can check that out. Every vertex is of degree greater than equal to 2. Okay, so now no need to check. You will simply say it is Hamiltonian. Okay, no need to check. It is Hamiltonian. Okay. Yeah. So if every vertex is of degree greater than equal to n by 2, then it is Hamiltonian. Now converse is not true. If graph is Hamiltonian, then every vertex is of degree greater than equal to n by 2. No, 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 no. Okay. One way theorems. Take snapshot. I will jump to the next slide.
Done.
Okay, so degree sequence of a graph is given. Is it Hamiltonian? So this is the good application. So number of vertices are 4. Okay, so number of vertices are 4. How we have got it? So I think you have got the idea. Degree sequence we have done in the previous lecture only. So first vertex of degree 2, 2, 3, 3. Okay, so I will say 4 by 2, that is 2. So every vertex is of degree greater than equal to 2 here, na? So I will simply say it is Hamiltonian. No need to draw the graph and all. You will simply say it is Hamiltonian.
With the facts.
Yes. Take snapshot. I will jump to the next slide.
Done, sir.
This is given. Is it Hamiltonian or not? 1, 2, 3, 4, 5, 6, 6. So 6 by 3, 6 by 2. That means 3. So every vertex is of degree greater than equal to 3. 100% Hamiltonian. Here is 1, 2, 3, 4, 5, and 6. 6 vertices are there. Is it Hamiltonian? So 6 by 2, that is 3. Every vertex should be of greater than equal to 3 degree. But here it is not.
But you have to.
So,
No, sir.
yeah, because we have 2. So can I say it is not Hamiltonian? No. That's why I have written here question mark. Okay, I cannot say yes or no. Are you getting it now?
No, sir.
Because I have told you so converse I'm going to ask na. So if the inverse I am going to ask. So degree u greater than equal to n by 2, then graph is Hamiltonian. So if degree u is not greater than equal to n by 2, then graph is not Hamiltonian. I cannot say. Are you getting it now?
Understood, sir.
From the logic, P implies Q, so not P implies not Q. I cannot say this is true or false. Okay,
Yes.
yeah. So that is the beauty of logic. So if you know logic, many questions directly you can solve. Take snapshot. I will jump to the next slide.
Okay, sir.
Next is Or's theorem. This has been asked in Get Direct. Directly it has been asked. So let G be a simple graph of order greater than equal to 3. For all u comma v, that means for all vertices, degree u plus degree v should be greater than equal to n implies G is Hamiltonian, and these all are non-adjacent vertices. Okay, so every pair of non-adjacent vertices, if you add their degree, that should be greater than equal to n, then we will say G is Hamiltonian. So for example, these two vertices are non-adjacent. Their degree you add degree 2 na, so 2 plus 2, that is 4. So it is greater than equal to number of vertices. Yes. So another non-adjacent are this. So 2 plus 2 greater than equal to 4. Yes. So every pair of non-adjacent vertices, their sum of degree is greater than equal to n. Yes. Graph should be Hamiltonian. So this is Hamiltonian for sure. Okay. No need to check.
Yes, sir.
Okay. So this is again one way theorem. Okay. Again one way.
Answer.
Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so here I have shown you some examples, what are Hamiltonian or not. Special graph phi of n, it is never Hamiltonian, but only one is phi 1. Phi 1 is Hamiltonian. Okay, so you have to cover all the vertices na. So trivially you have covered it. So phi 1 is Hamiltonian, but rest other are not Hamiltonian because they are not connected na. Phi 2 it is not connected. So from here how you will reach here? No way out. K regular, so it should be connected and K is equal to 2. Okay, it's K regular, it may or may not be connected na. so it should be connected and k should be equal to 2, that is for sure. Okay, for rest other I cannot say, like Peterson graph is 3 regular and it is not Hamiltonian. Okay, Peterson graph is 3 regular and it is not Hamiltonian. You can check that out. See this, Peterson is 3 regular.
Yes, sir. We have put it.
Okay, so every vertex is of degree 3, but still it is not Hamiltonian. Okay.
Yes.
Yeah. So next is complete graph of n vertices n greater than or equal to 3. Okay, it will be Hamiltonian. Why? Because k1 and k2 are acyclic. Okay, but still k1 is Hamiltonian. K1 is phi 1. Okay, k2 is acyclic, na? So it is not Hamiltonian. But k3 directly it is cyclic and it is Hamiltonian. ABC. Okay, k4 like this, gone. K5. Let me draw the k5 like this. So no need to worry. You simply scan from here. Okay, so you will say like this. You go. So we have a pentagon, na? So you just scan it. Game over. No need to go to other edges and all.
Sir.
Okay. So every complete graph of n vertices will be Hamiltonian, but n should be greater than or equal to 3. Next, cycle graph. 100% it will be Hamiltonian. C3, C4, C5. I think you have got it. C6. Everything will be Hamiltonian, na? Any doubt?
Yes, no.
Wheel graph. Every wheel graph is Hamiltonian. So it is also very simple. So let me write it here itself. So you start from here. Okay, you just go here. Okay, so you start from here. You
we
go
already
here
wanted sort of a
and now come again here and here. Okay, so second last time you just come in. So start from here, go here, now go here and here. That's it. Okay, similarly here also. You start from here, go here, here. That's it. So every wheel graph is Hamiltonian. Any doubt?
No, sir.
Okay, Qn. N is equal to 2 or 3. It has no comments because no necessary and sufficient condition. Because Q4, that is really very tough. It is very difficult to make. Q5, it is really very tough. Okay, so Q1, Q0 is this. Okay, so Q0 is Hamiltonian. Q1 is this. Okay, Q2 is this. Q3 is cube. You can check that out. They are Hamiltonian. Okay. Yes, bipartite graph. Bipartite graph I do not say. Okay, you have to give me the graph, then I can say. No comments. KMN, when mn greater than or equal to 2 and m is equal to n, when both are equal, okay, then it will be Hamiltonian, otherwise it will not be Hamiltonian. For example, complete graph, you take here 2 vertices and here you take 3 vertices. So now you here, go here. Now how you will reach here? No way. Are you getting it? It is a complete graph, na? So I am giving you the idea. So start from here, you here, go here. Now if by chance there is one more vertex here, then I will say okay, go here and then go here. Okay. So if equal, then it is okay. But if it is not equal, then we cannot say. Okay. So m comma n greater than or equal to 2 and m should be equal to n. Okay. Take snapshot. I will jump to the next slide. Okay, so this is important. This has been asked in GATE. So Hamiltonian circuit in Kn. Okay, so number of Hamiltonian circuits. Number of Hamiltonian circuit in Kn. If it is ordered, then n factorial. If it is unordered, then n minus 1 factorial by 2. If unlabeled, if complete graph is unlabeled, then we have only. This is unlabeled graph. Yeah, please come again.
Your voice was lost, sir. But I heard.
Okay.
Understood, sir.
Okay, so number of Hamiltonian circuit is in complete graph. So if graph is unlabeled, then it is only one Hamiltonian circuit. So like this, you just like this. Okay, but if graph is labeled A, B, C, D like this, and we are saying ordered, then it will be n factorial. but for unordered it will be n minus 1 factorial by 2. I'm not going into the proof and all, it will simply waste our time. So you just have to see whether they are saying ordered or unordered. Ordered means n factorial, unordered means n minus 1 factorial by 2. Or unordered means order does not matter. Okay, yeah, take snapshot and I will jump to the next slide. I will show you some examples.
Done, sir.
Okay, so how many edge disjoint Hamiltonian circuit in Kn? So okay, so I have not shown you, so you can make them. So for example, we have K4. Ordered will be 4 factorial, that means 24. Okay, for K4. Unordered it will be 3 factorial by 2, that is 3. Unordered is 3 and ordered is 24 for K4. Okay,
Done, sir.
unordered means order does not matter. Ordered means obviously order matters. Okay, so it's very simple, na. See, if you want a little bit proof, I will just give you the intuition behind it, why it is so. So ABCD, since it is a complete graph, so you write ABCD, you write ABDC, you write ADBC, whatever way you write, it will be a Hamiltonian circuit. You can check that out. Why? Because it is a complete graph. Between every pair of vertex there is an edge. So ABCD, this is Hamiltonian circuit. ABDC, ABDCA. Are you getting it now? ABDCA. I have not writing A just to give you the intuition behind it. Okay, because you will lost here. So better is I am just skipping the last vertex. Now ADBC, you simply check that out. ADBC, ADBCA. Okay, ADBCA. Okay, so whatever way you write, it will be Hamiltonian circuit. So that's why you simply arrange them. So arranging is n factorial. Is it okay?
Done, sir.
So unordered, order does not matter. So n minus 1 factorial by 2. So it will be only 3. You can check that out. Okay, take snapshot. I will jump to the next slide.
So in order, we have to say A, B, C, D, A, then like in that order only we have to write. Here
No.
order
Order
doesn't matter.
order means order matters. So all these are different. A B C D, A B D C, A D B C, all are different.
Yes, sir.
Okay,
And here
unordered means order does not matter. So so A B C D. Okay, let me write it. A B C D.
Once you write, it is exhausted. We cannot just write that in any
Again.
Sir.
You can think like that. Okay. Yeah, take snapshot. I will jump to the next slide.
Okay, sir.
Okay, so next is how many edge disjoint Hamiltonian circuit in Kn. So you have to remember the formula n minus 1 by 2 n minus 1 by 2 floor function. These are the edge disjoint Hamiltonian circuit in Kn. Okay, so for example in K4, so 4 minus 1 by 2 floor function, it will be only one edge disjoint Hamiltonian circuit. Okay, for K5 it will be 5 minus 1 by 2, that will be 2. So what are these two? So one will be star and another will be pentagon. These are the two edge disjoint Hamiltonian circuit in Kn. In K5. In K5, these are the two edge disjoint Hamiltonian circuit. Okay, so n minus 1 by 2 floor function.
Yes, sir.
Take snapshot. I will jump to the next slide.
Perfect.
This is very important question. Okay, so if you know the theory, then you will be able to answer it. Otherwise, you might not answer it. Okay, so the question is saying 9 person sits in a round table. How many arrangements are possible in which each person has different neighbor? So indirectly, they want to ask edge disjoint Hamiltonian circuit only. Edge disjoint, that means nothing, no edge is common. Are you getting it now? Edge disjoint means what? No edge is common. Okay, edge disjoint Hamiltonian circuit means disjoint means no edge is common. No edge is common means directly, indirectly, if A is neighbor of B here, then here A and B are not neighbors. Are you getting it?
Yes, sir.
Okay, so now they are saying like this only. 9 person sit in a round table. How many arrangements are possible in which every person has different neighbor? So edge disjoint Hamiltonian circuit only. So 9 minus 1 by 2 floor function 4 is the answer. Only 4 ways.
Yeah, sir. Because they can't sit beside
Yeah,
same
yeah,
line.
yeah. Okay. So take snapshot. I will jump to the next slide.
Done, sir.
Simple graph with n minus 1 C2 plus 2 edges is always Hamiltonian. I have told you na 4 one-way theorems we are going to study. So 3 we have done. So last was left. That means simple graph with n minus 1 C2 plus 2 edges is Hamiltonian. So what is the proof? Proof is very simple. I will say you take say 5 vertices. So n minus 1 C2 means 4 C2. 4 C2 means you will make K4. So 4 vertices, 5 vertices you are having, so you make K4. Now already you know every complete graph is every complete graph with 3 or more vertices is Hamiltonian. Okay, so this is Hamiltonian for sure. Now I'm saying plus 2 edges, and we are saying simple graph. So don't sir, you make 2 edges like this. Parallel edges are not allowed. So every now I cannot have more edges. Now we have exhausted all the edges. Okay, so what is the way? Plus 2 edges are there, so obviously you have to make like this and like this. Okay, so 100% it will be Hamiltonian. Why? Because this entire structure was Hamiltonian, and I have just added 2 edges, so one for going and one for coming back.
Yes, sir.
Okay, so for sure it will be Hamiltonian. So that is the simple idea, that simple graph with n minus 1 C2 plus 2 edges is always Hamiltonian. Any doubt?
No, sir.
Take snapshot. I will jump to the next slide.
Done, sir.
So next topic is planar graph. So let me check that out. What is the time? Okay, so we are having 10 minutes left. So okay, we start the topic. What is planar graph? A graph is planar if it can be drawn on a plane with no edges crossing. Okay, so there should be no crossover. That's it. So this is planar for sure. This you may argue, sir, it is not planar because there is a crossover. So no need to worry. So you take this edge like this. It is planar. Okay, so this, now please see this. This is a vertex, so there is no crossover. Don't say there is a crossover. There is not at all crossover. So like this is you can say roads. So there are 4 different roads. So they are just meeting here. They are not crossing over here. This is a big city like this. You can imagine. Okay, so this is planar. This is also planar. This is also planar. So planar means a graph is planar if it can be drawn on a plane with no edge crossing. Okay, take snapshot. I will jump to the next slide. Okay, what are the applications? So gas pipeline never cross each other because repairing one will damage other. Like CNG and PNG gas pipeline, they will never cross each other. Okay, once they cross each other like this, so if you try to repair this, this will be hampered. Okay, same is the case with electrical lines. They will never cross over. If they cross over, then obviously short circuit can be done and all. Okay, so while planning layout of these lines, we must avoid crossover by redrawing the graph. So like this, we have 4 cities. So what you will say, no doubt costing will be more, but you will take the pipeline like this, bypass kind of thing. Okay, so you will not do like this because it will hamper the things. Okay, but in some situations we can't avoid crossover even by redrawing the graph. Even it is even. Okay, even by redrawing the graph, and we must know what exactly are those situations. Okay, like this. So this was the graph. Okay, and we tried to redraw it and we have got a planar version, but some situations are there, even after redrawing we cannot make it planar. Okay, or we cannot avoid crossover. These are non-planar graphs. So obviously this point is saying we should exactly know what are those situations. Okay, so it's just like that. I give you a graph and you keep on trying that. Okay, can I avoid crossover? Can I avoid crossover and not, or not? Okay, but if you know that it is non-planar graph, you will simply say, sir, I cannot avoid crossover here. Okay, so you will try a different design of gas pipeline and so on. So this is the application. Are you getting it?
Answer.
Okay, so we should know exactly what are those situations. So let me jump to the next slide. Done?
Answer.
Okay, so how to check given graph is planar? So try to uncross the edges. That is the simplest way. Don't worry, I will give you theorems and all, but I am just trying to do that. So is this planar? Yeah. So how? So other edge was crossing now. So take it like this. Don't worry. Is this planar? Let me check that out. Pentagon. This is okay. And we have two more edges left. A, B, C, D, and E. So C to E is okay. D to B. Okay, I have done like this. Okay, and what about A to C? A to C will create problem. So now A to C I cannot go like this. Are you getting it? If I go like this, problem. If I go like this, problem. Okay, so let me try another method. Okay, so it is not working, so let me do it another way. So CE, A, B, C, D, and E. Okay, and okay, so in place of CE, you draw BD first. A, B, C, D, and E. Okay, so draw BD first. Okay, and then A to C. Okay, and then C to E, na? Yeah, we have got it. So this is planar. This graph is planar because I can draw it on a plane with no crossing.
Yes, sir.
Okay, yeah, so it is completely hit and trial. Na? In GATE exam, you cannot rely on hit and trial methods. So we have to study some theorem so that quickly you can solve and get the answer. So like this, here we were stuck. Okay, so we were not able to guess, so we try another way and we are able to guess it. But these are completely ad hoc ways or hit and trial ways, so we should avoid hit and trial method. So let me show you some theorems. Take snapshot. I will jump to the next slide. Done. Okay, so Kuratowski's theorem. What they are saying, Kuratowski's is the name of the scientist. So a graph G is planar. A graph G is planar if and only if it does not contain K5 or K33 as subgraph. Roughly I have said you. So exact definition or exact Kuratowski's theorem I will tell you in the next lecture, because now I think time is up. But no need to worry. I am just giving you an idea. Okay, so graph G is planar if and only if it does not contain K5 or K33 as subgraph. Subgraph we have not okay, subgraph actually don't worry about subgraph. You simply say that graph should not contain K5 or K33 in it. That's it. Okay, so directly I want to say K5 or K33 is just like a virus. If it is present in the graph, it will simply destroy it and it will say it is not planar. Okay, you can think like that. I have written here, see this, K5 and K33 are smallest subgraph which are non-planar, and if they enter in any graph G, then they becomes non-planar. That means they will act like a virus. So what is the advantage? Now you simply say it is planar, because neither K5 nor K33 is there. K5 is what? K5 is having 5 vertices and 10 edges, na? 5C2. 5C2 is 10, na? Are you getting it, na?
Yes, sir.
So K5 is having a K5 complete graph of 5 vertices. A complete graph of n vertices has n C2 edges. So 5 C2 edges, that means 10. So here you may say, sir, there are 5 vertices, but edges are 5, 6, 7, 8. Only 8 edges are there. So K5 is not there. K5 is not there. So obviously it is planar. Directly you will say in GATE exam it is planar. That is the power of the theorem. Okay. Similarly, K33 also. K33 is not there now because it is having 6 vertices, and here we have only 5 vertices. So no need to worry about K33. Okay. So see this both ways. Both ways I am saying if and only if. That means if graph is planar, then they are not there. And if they are not there, then graph is planar. Both ways you will say. Okay. Take snapshot. I will jump to the next slide.
Done, sir.
Okay. So now see this. So I will say this is K33. And here I have done some decoration and all, so it is not planar. Okay, because K33 is subgraph here. Similarly here you can check that out. This is this is K5. Okay, and here I have done some decoration, so it is not planar.
Yes,
okay, so K5 has 5 vertices and 10 edges. K33 has 6 vertices and 9 edges. I think you already know, na? K33 has 9 edges and K5 has 5 vertices. And K5 has 5 vertices and 10 edges. K33 has 6 vertices and 9 edges.
Nine
So
edges.
smallest non-planar graph in terms of vertices is K5, in terms of edges is K33.
Okay, sir.
Yeah, take snapshot. I will jump to the next slide.
Done, sir.
Okay, so corollary means some extensions we are doing. So extension is graph with less than or equal to 4 vertices is always planar. That is for sure. If graph is having 4 vertices or less than 4 vertices, it will be always planar because there is no question of K5 or K33 coming into the picture. Similarly, graph with less than or equal to 8 edges is always planar because if graph is having 8 edges, then there is no question of K33 or K5. K33 is having 9 edges.
9 edges, huh? 6
6
vertices.
vertices and 9 edges. K5 is having 5 vertices and 10 edges. So smallest non-planar graph in terms of vertices is K5 and in terms of edges is K33. So if graph is having, see 9 edges is in K33, na? So if graph is having less than 9 edges, that means less than or equal to 8 edges, it will be always planar. Similarly, if graph is having less than 5 vertices, that means less than or equal to 4 vertices, it will be always planar. Okay, that is what we have written here, corollaries. And they all are one way theorem, obviously. When graph is planar, then graph with less than or equal to 4 vertices is, we cannot say like this, na? If graph is planar, then it will be having less than or equal to 4 vertices. No, clearly no, big no. Why? I have shown you this only. It was having 5 vertices and planar. Okay.
Yes.
So any graph with greater than or equal to 5 vertices. Yeah. Okay. Take snapshot. Okay.
Done, sir.
Yes. So any graph with greater than or equal to 5 vertices, planar, non-planar, may or may not be planar. None. Obviously, may or may not be planar. I have to show you the graph. Without showing the graph, how you will comment about it whether it is planar or not? Are you getting it? So if I said less than or equal to 4 vertices, you will simply say planar.
Yes, sir.
Take snapshot. I will jump to the next slide.
Done, sir.
Any graph with greater than or equal to 8 edges, so may or may not be planar. But if they say less than or equal to 8 edges, then confirm it is planar.
Yes, sir.
Take snapshot.
Yes, sir.
Okay, so is this planar? So how many edges are there? 1, 2, 3, 4, 5, 6, 7 and 8. 8 edges are there. Yes, 100% is planar. No need to check. Okay.
Yes, sir.
So is this planar? A, B, C, D, E and F. Is it planar?
It is
Try
6.
to remember.
What is it,
This
sir?
was
Yes.
K33. It was K33 only, not planar. Okay. Yeah.
Yes, sir.
So take snapshot. I will jump to the next slide. Okay, so I think time is up. We will start from here itself in the next class. So in the next class, most probably graph theory will be over.
All right, sir.
Okay. Any doubt?
Discrete mathematics will go for some more days, sir.
Only one day.
Okay. Done,
Yeah,
sir.
graph theory is the last topic in discrete mathematics.
All right, sir.
Okay, yeah.
Yes. Thank you, sir. Good night, sir.
Okay, good night. Okay.